All right. So, whoever has a question, go ahead. I'm not sure where to start with this. Okay, Molly, if you have something you want to ask specifically, we could start with something, so we're not just sitting here watching us type messages to each other. Let's go through a quick. Yeah, which one? We can do any question you want. Same as it is a little. Same as in class, right? If nobody has any questions, we're not going to get anything accomplished. But if somebody I have mathematics all ready to go. If we have a specific uh, yeah, number 28. John wants number 28. Okay, so this is a good idea. We'll start somewhere. Okay, so I can't see the text while I'm on this screen right here, but that's weird. All right, we'll go to 29 and then go back. All right, so this is a pretty good place to start. So basically what this question is asking is it's saying use the circle shown in the rectangular coordinate system to draw an angle of 480 degrees in standard position. All right, so we have to sort of think about how big is 480 degrees? Well, I know that once around the whole circle is 360. So if you just take 480 minus the 360, we get 120. Okay, so now I need to go another 120 degrees. So we know that that much is 90. So if I subtract off 90, I know I only have to go 30 more. So you got to ask yourself, about how big is 30 degrees? Well, it's only about a third of 90. So I'm only going to go to there. So my angle would look like this. So the 480-degree angle will be all the way around the circle once, and then this little bit extra. Now, the trick to what we're going to start to do is we're going to start to think about the angles not like that. We're going to start to think about them in radians. And that's going to be a little tricky, right? But we could always turn this to radians. We can take 480 degrees times, and that's not what this question really asks, right? The question just asks which one of these is the answers, and this is a little bit cut off here, but you can see it's going to be that one. It's going to be B. But if we wanted to think about this in terms of radians, it would be 480 degrees times, I want to go to radians, so I'd multiply by pi over 180, and I would get 8 pi over 3. So ideally, as we move forward with some of these sections, is you're going to want to start to think about the angle not like 480 degrees, but in terms of a multiple of pi. All right, let's pop back over here to the questions. Anybody else have another question that we want to look at? Nothing. Nothing so far. Well, actually, let's do this. Let's jump over to. This was the thing that I made the video from, and let's go to this page, because if you get nothing else from this section, come on, getting a little glitchy. This is sort of the most important idea from this section, is that all the stuff that we're going to be doing in chapter 4, all the angles that we're going to be talking about, all the trig functions that we're going to be talking about, all the graphs that we're going to be talking about are pretty much going to deal with this picture right here. Notice that some of these angles may be familiar, right? Hopefully from geometry, you remember that there is whoops. a 30, 60, 90 triangle, and a 45, 45, 90 triangle, right? Those are our two special triangles with various ratios. And we'll get to the triangles in the next section a little bit more. But yeah. The way, yeah, there we go. The reason why we use these angles is because they're the two, or these angles, because these two triangles are the ones that are the most relevant in geometry. So basically, we're just going to be adding 30 degrees to get all of these different angles. And if you can obviously keep going, so this would be 360, and then this would be 390, and we would just keep going and going and going. But the idea is that we want to think about it with that number, with the pi over 6, with the measure in radians, because that's the one we're going to be using way more often. Let me see if I can go back to. So I want to just run how to make this again real quick, unless anybody else had a specific question. No, okay. So let me just run through this circle, okay? This is the beginnings of making a unit circle, okay? And so what a unit circle is, and actually, let me hold on a second. Let me see if I can pull up the chat on my other computer. Yeah. Let me just hold on. Oh, yeah. Okay. Yeah. Well, that didn't work. All right. Whatever. I was trying to pull up the chat on my desktop as well. Okay, so let's just go through real quick how to start making the angles in a unit circle. We'll do it first in degrees and then it's in radians. So we're going to start with 0 degrees right there. Okay, then this is 30 degrees. That's a 30-degree angle, right, from there to there. So if we add another 30 degrees, we get an angle that's this big plus another one. So we would go all the way to there. Looks about right. If that's from there to there's 30, looks like that's another 30. So that would be 60. Then we keep adding 30, 150, 180, 210, 240, 270, 300, and 330. Okay, so now we basically made every multiple of 30 degrees all the way around, and this could also be 360, all the way around this circle. And again, these are the angles that are going to be the most important. These are the angles that we're going to find coordinates for, that we're going to find trig values for in the next couple sections. We need this middle one in here, right? And that's halfway in between 90 and 0. So that's my 45-degree angle. 45 plus 45 is a 90. Then 135. Then 180. Then 225, 270, and 315. Okay? So those are the basic angles in degrees. That's the easy part, right? The harder way, or the more complicated, or not even complicated, the thing that we have to start to think about, the thing that we have to start to retrain our thoughts is that we don't want to use degrees. We want to use radians. So we can start with 0 radians. 30 degrees in radians, if you don't remember, we take 30 times pi over 180, and that gives me 30 pi over 180, which reduces to pi over 6. So this is pi over 6 radians. Now, a little symbol, radians is unitless. Remember, it's a ratio between the arc length and the radius. And the reason why there's a pi in there is it all comes from the circumference of a circle, which was 2 pi r. All right, so we have this value right there. To go from 30 to 60 to 90, we just kept adding 30 degrees. Well, if 30 degrees and pi over 6 is the same thing, which they are, we can just keep adding 30 degrees, or keep adding pi over 6. Well, pi over 6 plus another pi over 6 is 2 pi over 6. But you don't write it like that, right? We reduce it, so it turns to pi over 3. Well, that's 1 pi over 6, 2 pi over 6. 3 pi over 6 would reduce to pi over 2. And then 1, 2, 3, 4 pi over 6 would reduce to 2 pi over 3. 5 pi over 6 doesn't reduce, and 6 pi over 6 reduces to pi. Okay, there's half our angles all the way around this circle. Let's keep going. So that's 6. 7 pi over 6 does not reduce. 8 pi over 6 reduces to 4 pi over 3. 9 over 3 reduces to 3 over 2. 10 pi over 6, or 9 pi over 6, or yeah, 9 pi over 6. 10 pi over 6 reduces to 5 pi over 3. 11 does not reduce, and now we're back to 12, which is 2 pi, which is once around the whole circle. All right, so those were the 30-degree angles. Next comes the 45. If you can't remember, right, 45 pi over 180 reduces to pi over 4. Okay, now let's do the same thing we did with pi over 6. We start with pi over 4, that's 1. 2 pi over 4, right? For another 45 degrees, it's 2 pi over 4. 3 pi over 4. 4 over 4 is 1. 5 pi over 4. 6 over 4. 7 pi over 4. And then 8 pi over 4 would be 2 pi. So what we just did right there was we made the most important, and we didn't make every angle, right? Where's 25 degrees? Where's 15 degrees? Where's all these other things? These are the most important, okay? These, how many are there? 1, 2, 3, 4, 6, 9, 10, 12, 13. These 16 angles are going to be the basics of how we evaluate trig functions at specific points exactly. We'll get into a little bit how to do it on your calculator, but this is the basics of what are the angles that we consider in trigonometry to be the most important. And with all of these have coordinates. Now, that coordinate would depend on the radius, right? So this would be the radius of the circle. So this coordinate right here would depend on how far away from the origin you are. And we'll get into that for a specific circle where the radius is equal to 1 in the next section. And that's called a unit circle. So this is all building to something called a unit circle, which we could then use to really work with any circle, because no matter what, when I make a circle, let me move it down a little bit. Right, when I make this circle, I can't make it bigger. Yeah, I can. All right, so when I make this circle bigger and bigger and bigger, right? No matter how big I make it, this angle is still the same, right? The radius is different, but this angle from here to here is still going to be pi over 6. It's still going to be 30 degrees. So as long as you have a central angle, as long as you are starting in the middle of a circle, right, the angles that these trig functions make don't really change, right? It's still how far around the circle you go. It's still to get from there all the way around, it's still 360 degrees. It's still 2 pi radians. So no matter what, those angles don't change. The only thing that's going to change is the radius for different types of circles. But that's kind of an important idea, how to make the beginnings of our unit circle. All right, what else we got? Who else wants to ask a question? Okay. No one's asking anything. Let's see. What is a good question? Coterminal angle, right? We just have to add 360 or subtract 360 to get a positive angle in between 0 and 360. Or with radians, right? We add or subtract 2 pi, right? This is clearly bigger than 2 pi, right? 16 over 8 would be 2 pi. So we're just going to keep subtracting until we get a number between 0 and 2 pi. Because if you think about the way the circle works, right? If I go once around or twice around, right, I'm still going to wind up there. Once around, twice around, right? I still wind up at pi over 6. It's going to be not 30 degrees anymore. It's not going to be pi over 6. It's going to be pi over 6 plus 2 pi or minus 2 pi. But the point is that this coordinate, that place where the angle intersects the circle that we're spinning around on, means that the coordinates are going to be the same. You're still, the terminal side of the angle is still in the same spot. And that's going to be important as we deal with other types of angles later. Arc length is pretty easy to calculate, right? It's just the radius times theta. The only thing is that theta must be in radians. So don't multiply 17 times 75. You got to take 75 times pi over 180 first before you convert it, or before you multiply it. Probably the toughest questions that people have every year are these ones at the end with the conversions. Molly, which particular problem were you looking at? One like the arc length, or do you want to go to some any of them? Okay. Well, let's do an arc length problem. So the way I would do this problem, right, is the formula is that arc length is equal to the radius times theta. Okay, but it's important to remember that theta must be in radians. That is not in radians. That's in degrees. So arc length is going to be equal to 17 inches times 75 degrees, but I have to change the degrees to radians, so I multiply by pi over 180 degrees. The degrees cancel, and the only unit left is inches. Well, it's an arc length, okay? Radians is unitless, right? We don't need a unit for a radian, so basically, I just have to take these things, multiply them together, and type your answer in terms of pi. So that means I don't even have to put in 3.14. So I just take 17 times 75 divided by 180, and it gives me, does it say fraction? Use fractions. So 85 pi over 12 inches. And they put the inches there for you already. Okay? So for arc length, all you have to do is follow this formula and just remember the trick that the angle has to be in radians. All right. We'll do another one. Let me do one of these conversions right here. And that is what happens when you have some sort of angular speed. Why did that not work? There we go. Okay, so when we have angular speed, I want to turn revolutions per second to radians per second. And there's only one real conversion that you have to remember, and it's very simple. And it's that 2 pi radians is equal to 1 revolution. All the way around the circle is 1 revolution around the circle. Okay, so if you have 5 revolutions per 1 second, okay, hopefully, I know this might be a lot to ask, but hopefully you guys remember a little bit of the dimensional analysis from physics, where wherever you are trying to go, just cancel that thing by putting it on the opposite side. So if I want to get rid of revolutions, I use this conversion factor, but I use it with revolutions on the bottom because I want it to cancel out. So I just multiply by 2 pi radians. I can actually write radians if I want to over 1 revolution, but just don't get confused by writing radians because it is really unitless. But sometimes, especially for this problem, they want to write it. So we just revolutions cancel. Type your answer in terms of pi. So this is going to be 10 pi radians per second. Seconds are already on the bottom, so we don't even have to do anything too crazy for this particular problem. There was one. Let me pull up the one that I did in this section near the end, because this one's a little. This is the type of problem that I would normally like to put. Obviously, complicated. All right, so this last one right here. This requires a longer dimensional analysis, but it's not too bad. So as long as you remember the formula, that all you have to do is take the radius times the angular speed, and that is equal to linear speed. So linear speed is equal to the radius times omega. Looks complicated, it's really not. So omega is just the angle over the time. Okay, so we know all those things. Well, okay, little trick here. They put diameter instead of radius, but we can easily change the radius or the diameter to a radius, right? It's just 22.5, half of that. 390 revolutions per minute. That is omega. So omega is 390 revolutions per 1 minute. All I do is multiply these together, okay? So my linear speed is just inches. So be careful with the unit. The trick here is units. All right, so it's 22.5 inches times 390 revolutions in 1 minute. Okay, so that would actually be my answer if I wanted it in inches revolution inches per minute. Right, multiplying these, divide out the minutes. That's a weird way to measure speed. Okay, most commonly miles per hour. Okay, so now all we have to do is just keep multiplying by stuff to convert this inches revolutions per minute to miles per hour. So let's start with the revolutions. And we know that there's 2 pi radians in 1 revolution. That cancels out the revolutions. And that's good because now I have something that's unitless that's not going to affect my measurement at all. Okay, I don't want inches, so I got to get rid of inches. Well, you should know this one, that there's 12, whoops, right? I want inches to go away, so I put it on the bottom. So there's 12 inches in 1 foot. That's an easy one. The harder one to remember is that there are 5,280 feet in 1 mile. And now I have inches cancel, feet cancel, right? Now I have miles per minute. That's not what I want. I want miles per hour. So I just want minutes to go away. So there's 60 minutes in 1 hour. So now minutes cancel, multiply across the top, multiply across the bottom, and divide. So it's just a matter of 22.5 times 390 times 2 times pi. Don't forget about the pi. Times 60 divided by 12 divided by 5,280. And if you did all that on a calculator, you should, if I remember, get 52 miles per hour. Okay. Let's see if anybody asked something specific. I think you could do it. It's obviously going to be harder. Molly, if you need more help, you could always email me some stuff, or I can make you videos of specific problems that you're having trouble with. You want to do another problem with the dimensional analysis like that? That one was actually more complicated than you would probably see. Let's do one that's a little bit easier. Let me pull it up from the textbook. Hmm. All right, let's look at this. That one was for a previous one. Let's look at 92. The radius of a wheel rolling on the ground is 80 centimeters. If the wheel rotates through an angle of 60 degrees, how many centimeters does it move? Okay, so that's a linear distance. Express your answer in terms of pi. Actually, that's just arc length, right? So if we know, this is actually easier than I wanted to do. The radius of a wheel rolling on the ground is 80 centimeters. If the wheel rotates through an angle, how many centimeters does it move? So we're basically looking for the distance around the circle that it has actually moved. So it's distance, not speed. Okay. So the arc length is always going to be equal to the radius times theta. And that's the radius, that's theta. But don't leave 60 degrees in degrees. You have to turn it to radians. So arc length, or sorry, arc length is equal to 80 centimeters times 60 degrees is one of those numbers that you should kind of get used to transferring to radians. It's pi over 3 radians. Okay, so 80 divided by 3 doesn't reduce. So to leave your answer in terms of pi, it's just 80 pi over 3 radians. No, sorry, centimeters. Okay. That's in terms of pi. That doesn't make a lot of sense because that's not how we measure things. So you would could actually multiply that out to give you 83.73 centimeters if you just multiply 80 times pi and divide out the 3. Let's try one with the yeah, we can do as many live streams as you guys want to show up for. So we can do these every couple days if you want. What number do we want to do? 40. Okay, 40. Good. I was on that. All right, let's see what this one's like. The minute hand of a clock is 10 inches long. That's the radius. So if you can imagine the minute hand of a clock, it starts in the middle of the clock and goes to the edge. So my 10 inches is the radius, and it moves from 12 o'clock to 1 o'clock. How far does the tip of the minute hand move? Well, the tip, right, here's the clock, here's the minute hand, and it's going to go, that's arc length, right? So we want to know this distance. So in order to do that, we need the radius times the angle. I got to figure out the angle based on that. Well, 12 to 1 o'clock, if the, and I could do this in degrees, but I'm going to challenge you not to, right? Try to go right to thinking about radians. All the way around the circle is 2 pi radians. There are 12 numbers on a clock. So to go from 12 to 1 o'clock, that's 1/12 of the way around the circle, right? You're going 1 hour, right? There's 12 hours on the clock. So this is pi over 6 radians, 30 degrees. Okay. If you would take 360 degrees, split it up into 12 pieces, you would get 30 degrees. Okay. So now that I have my arc length or my angle, arc length is equal to the radius times the angle, pi over 6. Type your answer in terms of pi. So this is 10 pi over 6, which reduces to 5 pi over 3. Okay, so that's number 40. We're going to do the podcast at 2:15. The meeting with Dr. Gemmarella got moved to this afternoon, so I can't give you a preview of any new information that we got, but we'll be on there and we'll share everything that we learn with you guys. So we're not trying to keep anything a secret. We want you guys to be informed with everything that's going on. So we'll try to do those podcasts every day. I know Trista said she was going to come onto this one, hopefully. So we'll try to have a guidance counselor. Richardi and I will usually be on there every day, and we'll try to have a guidance counselor and any other teachers who want to join. So we put it out to everybody. So we're going to try. Listen, we invited everybody. So whoever wants to come, they can come. Any more specific questions about math? 44. Okay. This is DMS notation, degrees, minutes, seconds. Now, there's a long way to do this and a short way to do this, okay? The long way is to say that we have, come on, there we go. Okay, so that means we have 43 point something, right? I have this 50 minutes and 14 seconds. Well, because I'm going to degrees and minutes and seconds, I take the 14 seconds and I divide it by 60, which gives me a decimal. It gives me 0.23, which now means I've changed this by dividing it by 60. I've changed it to a minute. Okay, so now I have 50.23 minutes divided by 60, and I get my decimals. So it's 43.8372. Okay, that's the long way. The simpler way is that somewhere on your calculator, there's either this, or if you have the Silver Casio like me, there's a button underneath the square root that looks like this, okay? And this is all in one button, right? if you just press this button, it'll convert to degrees, minutes, and seconds for you. So in this case, you would type in 43, press this button, 50, press that button again. It won't give you this symbol. It won't give you the minute symbol. It'll give you another degree symbol, but it'll fix it when you press equals. 14, press it again, press equals, and now you see it as just like this. If you press this button a second time, it'll convert it to a decimal. And if you keep pressing that button, it'll go back and forth between degrees and decimals. That's what this is called. And degrees, minutes, seconds, which is what that one is called. If you don't have the Casio, if you have like a TI or something like that, it's in there somewhere. It's in one of the menus. You got to dig around a little bit or watch a YouTube video and figure out how to get your calculator to convert degrees, minutes, and second notation. Or you can do it by hand. It wasn't that bad. You just got to remember that there's 60 minutes in a degree and 60 seconds in a minute. What else? Everybody is feeling mostly confident with this first section? Okay. Unless somebody has something specific, I'll end it there. Unless you guys want to ask another problem or go through another idea or talk about anything else. Bridget, go outside. You can go outside to stay away from people. Go for a run. Get some exercise. That'll keep you healthy. It's weird walking down the street and seeing my neighbors and like, you know, waving at them from like across the street. But as of right now, again, we have our meeting with the principal at 1:30. That's good. We have the meeting with the principal at 1:30. We are probably, if you couldn't tell, like we were one of the last schools to close. We're probably going to do what the governor recommends because we're a county school. So right now the governor has closed everything until next Monday, or not the 23rd, the 30th. So right now we're closed this week and all next week for sure. The governor said the 30th things are up in the air. We're gonna do sort of what he recommends. So if he says that schools can reopen, we probably will, as opposed to some other school districts that are closed for longer. We're gonna go with the state. I know it's weird, right? You guys thought you wanted more time off, and you realize that you miss everybody. And listen, there's some really bad. Bridget, you can go to school and pick up breakfast. You can't go to school and have breakfast. You walk in the door, they'll give you some breakfast, and you take it to go. And we talked about the productions yesterday. Like these are going to take a hit, right? We're going to have to figure it out as a department, like who can go when and who's going to be ready for what, depending on the day we get to go back to school. Molly, it depends. It depends a lot on you guys, on whether or not you guys say you're ready to do it by a certain day, and what Shep and Jesse decide that they want to do with that. So, you know, remember that I have 2 little kids. So right now, my wife is entertaining them while I'm on this call. Then she has a call in the afternoon, and then I have my call again with and our podcast with everybody. So we're like taking turns. Yeah, I'll bring them on. We're taking turns, sort of keeping them sane and trying to keep each other sane. The problem with teaching the lessons like this is I don't know exactly how long they take. A little bit longer, right? So the video was an hour and 10 minutes. I I could try, and I'll go back over anything that you want in these little sessions, but not everybody can come to these. There's only 8 people in here. Our class is 26 people. A house tour? My house is not that exciting. This is my office that I get to sit in. I'll show you guys my office. Hold on a second. What is it? Oh, there it goes. All right, so thankfully it is not that close, or at least it's not this space, which is absolutely out of control with much chaos from the kids. So we try to keep most of their stuff down there and give them a space to play. All right. I think that was mostly it. Anybody have anything else? I don't know why. It's a little pixelated here, but oh, I know why. Because I went off the wired internet to the Wi-Fi. Okay. So I'm gonna cut this off, and I'll post it in the classroom for anybody else who wants to come look at it later. The link for the podcast is in Google Classroom in the I know Miss Alvarez has a crazy ceiling. Yeah, the link to the podcast will be in the Google Classroom, and maybe I'll see you guys this afternoon. All right. So have a good day. I'll put a new lesson probably not this week, probably Sunday night. So I'll put that in classroom. All right. Take it easy, everybody.